So a series is a sequence where instead of I have commas between numbers. Instead of commas, I replace them with plus signs, and I add them all up. In a nutshell, that's what a series is. Now, typically we'll use sigma notation for a series. And we might say that, okay, this goes on forever. And then really the question is, does this make any sense? Now, as I've written this out, it doesn't really make a whole lot of sense. So let's try to think about how to make a sequence out of a series, which of course is made out of a sequence. What you want is you want the sequence of partial sums. So how does that work? So let's start with this. Let's start with any sequence you like. Let's start with a sequence. I'll say the sequence is A and the terms are AN, so N is my index variable. And so the terms of this, of course, are A1, A2, A3, and so on. Really what I'm interested in is the sequence of partial sums, and what those are is that I add up the first few terms and then I stop. So the first partial sum is just A1, adding nothing. The second one is A1 plus A2, adding the first two terms. And then the third one is A1 plus A2 plus A3. And I think you might see the pattern now. And so I might call this guy here S1, this guy S2, this one S3, and this one S4. I now have a new sequence, a sequence S. That's the sequence of partial sums. You can conveniently write this with sigma notation, and I suggest that you do. S, well, I've got now two indices involved, so let me call this one SM, is the sum from 1 to m of AN. Now, there's a lot going on in terms of indexing here. So this, I'll mark in blue the n's. These are the n's. And let me mark in red the m's. But the thing to notice is that the m's also show up in the top one because they're the last term in each of our partial sums that we're using. And so you can keep track of where you are in the partial sum by seeing the last term that you've added in. Okay, well, so short answer then is we say the series converges and that means that if the sequence of partial sums converges. We write, well, we're going to write the limit as m goes to infinity of Sm. That's the limit that the series would converge to. That is the sum as, in fact, let's write it out this way. Here's just expanding the notation, and here's the new notation. The new notation is like this. And we'll say that this is the value of the series if it exists. Now, finding the values of series and whether they converge or not is actually a surprisingly difficult task. It's just about as hard as computing integrals. But fortunately, you can use integrals to actually figure out if series converge, and actually vice versa, because these kind of work a bit like Riemann sums. Remember those? But we're going to spend the next few videos working on those. But for the moment, let me just point out a few good examples here. I have a separate video that explains what's a geometric series, and what it converges to and when it converges. A geometric series is a sum that's of the form 1 plus r squared plus r cubed plus r to the fourth plus many other possibilities, r to the n, or any multiple of this. So you can take this whole guy and multiply it by some constant c. If you want to write it out in sigma notation, that's totally fine. It's convenient to index it starting at 0. And so geometric series converge when the r is small enough. Specifically if the r is less than 1 in absolute value. There's a separate video on that. Okay, so geometric series converge. Here's another series that's a little harder to work with, and it looks like it ought to converge, and students always think that it ought to converge. Heck, I thought it ought to converge when I first saw it, but it does not. It is kind of crazy. This is the harmonic series. And if it had a value, it would be this, but this diverges. I will leave it to you to find a proof of that. There's a variety of them, some of them quite clever, some of them rather simplistic, to figure out why the harmonic series diverges. But if you really want to irritate a calculus professor, just go tell them that the harmonic series converges and watch them writhe in anger.